Today we'd like to look at the Vesica Pisces shape, which is very important not only in artwork. You tend to have ancient drawings and carvings with this shape, including the Buddha and including Jesus Christ. And sometimes I've seen the Virgin Mary in pendants with that shape. But there's actually very important building and construction information in this shape, including 1, square root of 2, square root of 3, square root of 4, which is 2, and square root of 5. So even though those numbers are infinite, when you punch them in a calculator, builders and people who were making constructions were able to use this shape to create those specific dimensions, as well as 30 degrees, 60 degrees, 90 degrees, and even 45-degree angles. So they're very common, as you see everywhere you look. Every building is standing at a 90-degree angle or perpendicular to the ground. So when we're finished, we'll have something like this. We're going to be able to see this distance as 1, 1, 1, 1. So that's a square, and on the bottom there's a square. And if you've understood the Pythagorean theorem, you have 1 squared plus 1 squared equals square root of 2. And we can show that as we go. When we connect from here to here, you have 1 squared plus 2 squared equals square root of 5. The distance from the bottom to the top of the Vesica Pisces, the little egg part, is square root of 3. And this is 1, or 1, so then 1 plus 1 is 2, which is square root of 4. So this distance here would be the square root of 4. So let's take a look at the Vesica Pisces and how it's a master builder's friend. So in order to construct the Vesica Pisces, we're going to simply draw 2 circles. So I'm going to put my compass point down. If you want it to be centered, you would basically have the center of your paper in between your compass and your pen. And you're going to draw 1 circle. You're going to then place the compass point on the edge of your circle and repeat. So one of the reasons the compass has a pointy tip is to be able to see centers, so that here and here I could see the markings where the compass was indented, because we're going to use those 2 spots. So to make the Vesica Pisces, that's it. You just draw 2 circles. As far as getting all of that other information, we need to do a couple more things. So the first thing we're going to do is we're going to draw a line straight down from the top of the egg to the bottom. And in fact, that'll give us square root of 3 compared to here being 1. So if the the radius of this first circle we made would be from here to here, that's this amount. That would be considered 1. So then this will show you, even algebraically, how this is going to be square root of 3. The next thing we want to do is we want to connect the 2 dots that I had colored where our compass was touching the center. And in fact, we kind of want to go a little bit past that, because we're going to be making a 90-degree angle. So we need a little bit of room there. So for this next step, I guess I'll use a pencil, since we don't really need to have a record of it. We can erase it afterwards. But the next thing we need to do is we need to find a line parallel to this one going straight up and down here, so we can make the box. So what I'm going to do is I'm going to first make a circle so that there's even spots on both sides of the center point here. So I'm going to draw here and here. If I want, I could draw the whole circle, but I'm going to erase it, so I won't do that. Now that it's even, we can cut the line in half or perpendicular bisect it, and it'll give us a 90-degree angle. So I'm going to open my compass a little bit more than the center. Put 1 point on the edge on the right, and I'm going to make an arc on the top and bottom. And then I'm going to go to the other side and repeat that. Having done that, we'll be able to draw a straight line going 90 degrees or perpendicular. And we want to go to the very edge of the circle. So here and here. We're going to repeat that on the other side. We're going to get two even spots and then make a perpendicular bisector. So it doesn't matter how far open your compass is. I'm going to make a mark here and here. So the two marks are the same distance from the center. Now I'm going to open my compass a bit, put the point here, and make an arc. So we're doing the perpendicular bisector construction to cut a line in half. And where the two arcs meet are where we line up our ruler. So to finish, we're going to connect the two spots on top and on the bottom to make a rectangle or two squares. So it's also a rectangle that's special because the rectangle has two squares, or the length is twice the distance of the width. So let's take a quick look at some of the things we have here. And I'll try to use some colors for that. So the first thing we had mentioned is the center. From here to here is square root of 3. And we can prove that using, if I wanted to prove it, I could use a triangle here. So what we have here is a 30, 60, 90 triangle. Here's 30, here's 60 degrees. And to prove that, we're going to... So I'm going to adjust my compass back to the distance from this point to the middle. So for a moment, we're going to look at just this triangle. Here's 1. And we're going to see how this is 1, 2 times the size. 1. Let me make a mark so you can see. From here to here is 1. From here to here is 2. So what we have here is a 30, 60, 90 triangle. As those of you who understand and have learned that, you know that the small side is 1, the hypotenuse is 2. So this long side is square root of 3 because 1 squared plus whatever this one was, x squared equals 2 squared, Pythagorean theorem. So 1 plus x squared equals 4, subtract 1, x squared equals 3, square root both sides, x is square root of 3. So this proves that that line from here to here is square root of 3 if this was 1. Well, we're counting this, double that as 1, so double it is going to be the square root of 3. Next, we want to look at this length. We could use our compass kind of like a ruler to measure distances. So from here to here, we said is 1, and then up here is the same amount, on top's the same, and on the bottom's the same. So this is a square because all the sides are the same. So if all of the sides are the same, then the diagonal of a square is going to be square root of 2. And it's going to create a 45-degree angle. And so the reason for that is we had learned, again, the Pythagorean theorem. 1 squared plus 1 squared equals the hypotenuse. Well, 1 plus 1 is 2. So 2 equals x squared, or the square root of 2. So the diagonals of squares are always square root of 2. And they make 45-degree angles. Next, what we have is the square root of 5. So the square root of 5 is going to go from this diagonal to the other diagonal, or from this corner to this corner diagonally. And that's going to be the square root of 5. So again, this is 1, so this is 1. Well, then down here would be 2. So let's take a look at that. So this is 2, and then from here to here would be 1. So let's find this diagonal. Again, we're going to use the Pythagorean theorem. 1 squared plus 2 squared equals x squared. 1 squared plus 2 squared equals the hypotenuse squared, so 1 plus 4, or 5, equals x squared. Square root it, x equals radical 5. So, you know, technically we're saying from here to here is 1. So that's the square root of 1, right? Because the square root of 1 is 1. And the final part, or actually, since I'm mentioning square root of 1, I might as well mention the square root of 2. So over here, or square root of 4, here we said it's 2, right? 1, 2, it's twice the distance of the starting radius. So square root of 4 is 2. So we have square root of 1, square root of 2, we're missing square root of 3, or no, it's right here. I just didn't write it down. And then square root of 4 and square root of 5. So we have the square root of 1, 2, 3, 4, and 5. We also have the golden ratio, phi. We're going to take the golden ratio is going to be 1/2 plus the square root of 5 over 2, or 1 plus square root of 5 all over 2. And it's going to be, I believe, 1.61. It's the golden ratio. So the way we get that is pretty easy. Because we want the square root of 5 over 2, well, here's the square root of 5. So let's take half of it over 2, plus half. Half would be here, plus this amount. So I'm going to open my compass from here to here. So that it's open square root of 5 over 2, or half of square root of 5. And I'm going to draw that arc down here. So when I readjust my ruler, maybe I'll pick another color. I can find brown. I'm going to adjust the ruler of the line that was going this way and extend it to here, to that spot. So from here to here was square root of 5 over 2, half of it, this amount. Plus this amount here was half. So this line right here is going to be phi, or the golden ratio. So the Vesica Pisces really is an amazing shape, not only for the balance and the beauty of it, but if you're a mason, and in the old days, everything was done with a compass. There were no computers, obviously. The only way to build something was to use a compass, and we can now have square root of 1, square root of 2, square root of 3, square root of 4, square root of 5, 30, 60, 90 triangle. So we have 30 degrees, we have 60 degree, we have 45, 45 angles, we have 90 degree angles. Obviously there's here and here the right angles. So you can build a house, you can build any structure now, because you want it standing straight up with gravity pushing down on it. If it's leaning over and not 90 degrees, gravity will push it down like the Leaning Tower of Pisa. So now we can build things that are strong, solid, and balanced. If you look at the corner of a paper, the house standing, things, a pole, things that are 90 degrees are structurally sound and work well with gravity. So this is the Vesica Pisces. And a little bit of algebra to show you how we get square root of 1, square root of 2, square root of 3, square root of 4, square root of 5 from this shape.